In today's lesson, we are going to be looking at permutations with non-ordered elements. So this is going to bridge the two units that we're looking at, and it's going to kind of basically finish off our last little bit of permutations and then carry us over into our new unit. So first, just a little bit of review. How many arrangements of each of the following words are there? So if I wanted to take the letters in each word and arrange them, how many ways could I do that? Well, fail, F-A-I-L, there are four options. So there's essentially four spots. If we're using the slot method, 4, 3, 2, 1, or 4 factorial ways that I can arrange those four letters. Now, what about fall? So fall is a little different because, and we'll go through and we'll look at some of the actual ones. If I had F-A-L-L, that's one arrangement. Let's maybe do F-A or F-L-A-L or L-F-L-A, something along those lines. But what if I did L-F-L-A and said, well, it's just the two L's that are different, right? I have two L's, right? Maybe if we color code this, maybe make the second L red. Oh, well, they're in different spots, right? I have two different L's. I put them in different spots. Is there any difference between these two? LFLA, LFLA. I mean, yes, the color, just to indicate which L I'm using, a first or a second one, or just the fact that we have two of them. But is there an actual difference between how they're arranged? And the correct answer would be no. There is no difference, right? LFLA, LFLA, same letters, same arrangement. It looks the exact same. So this is the situation that we're going to be looking at when we're dealing with permutations and what our new unit is going to focus on. So looking at this, there is no difference here. So I can't just do 4 factorial again because I have to take into account that we have some objects that are similar, which is going to affect the order. So when we have non-ordered elements, so in general, if there are n objects to be arranged, where A, B, and C objects are alike, then the permutation formula is n factorial divided by A factorial times B factorial times C factorial, so on. Basically, we're dividing by the number of items that are the same. So if I go back to that fall example, F-A-L-L, I had two L's that were the same. So in general, if assuming that all the items were separate or unique, it would be 4 factorial. But I'm going to divide now by the number of objects that are the same, which in this case is 2 factorial. So 4 factorial divided by 2 factorial, that would give me the number of arrangements, right? Because I have 2 L's. So we're dividing by the number of objects that are the same. So how many arrangements are there of the following words? Color and Mississippi. So color, again, we can see that in color we have two letters that are the same. The O and the O, or we have two O's. So I have two O's, so I'm going to imagine that all the items are unique. So I have 6 items, so 6 factorial divided by 2 factorial because the two O's are the same, and I get 360 ways. Now, with Mississippi, there are multiple items that are the same. If I go through and look at it, I have 1, 2, 3, 4 I's. I have 1, 2, 3, 4 S's. So 4 S's, 4 I's, and I have 2 P's. So in this case, again, how many items in total do we have? Well, we have 11, so 11 factorial, assuming they were all different. But I'm going to divide by 4 factorial times 4 factorial times 2 factorial for the letters that are the identical objects. So the 4 I's, the 4 S's, and the 2 P's. I'm going to divide by that, and in the end, we get 34,650 ways. So again, we're taking into consideration the items that are the identical, where we wouldn't be able to tell the difference, dividing by that factorial, which would then account for the arrangements where the 2 or the 4 S's might be in the same location. So even though we might think that they're different, they would appear not. So the next example. So 5 identical math textbooks, 6 identical science books, 3 identical geography books are on a shelf. And how many ways can they be rearranged? So again, we want to think of a couple things. One, because we want to think about how many ways can they be rearranged, we are looking at an order. Basically, how many ways can we order these books? But we also have to keep in mind that we have identical math books, identical geography books, science books, and then identical geography books. So you can imagine, assuming these are textbooks, how many ways can we arrange these textbooks? Right? If they're all the same textbook, are we going to notice a difference? Right now, you may argue, yes, well, so maybe more damaged than others or worn out. But assuming they're all brand new textbooks, straight out of the packaging, straight from the manufacturer or the publisher, we can't tell the difference. Right? So in total, we have 14 total books. So 14 factorial divided by, well, we have the 5 books, or the 5 math books, so divided by 5 factorial, divided by 6 factorial, and lastly divided by 3 factorial, right, for the different books, or the different identical objects. And when we calculate this in the end, 168,168 ways. So again, by dividing by those factorials, we are taking into consideration the arrangements where we have the math books in the same spot. Even though they might be a different book, it might appear the same though. Example 3. So Katie is laying out tiles for a mosaic edge. How many patterns can she make if she uses 4 yellow tiles and 1 of each blue, green, red, and gray? So again, the key thing here, we're trying to make a pattern. So when we're dealing with a pattern, we're trying to make an order, but she's also using 4 yellow tiles. So again, it's implied that these are identical. So now we have to kind of, if we're reading the question, we have to think about, do we have objects that are considered identical, where we can't tell the difference? So again, to calculate, first we need to figure out how many objects we have in total that we're arranging. So we have 8 total objects, 4 yellow, and then 1 of blue, green, red, and gray. So we have 8 factorial divided by 4 factorial because of the 4 yellow tiles, which gives us 1,680 ways, or 80 patterns. We'll use patterns just because, again, from the question. So 1,680 patterns. A contractor wants to plant 6 oak trees, 9 maple trees, and 5 poplar trees along the subdivision street. The trees are to be spaced evenly apart, and in how many distinguishable ways can they be planted? So again, key phrasing here, distinguishable ways. So how many ways could we clearly identify a difference? So because we have the different trees, 6 oak trees, the 9 maple trees, and the 5 poplar trees, it's assumed or it's implied that I wouldn't be able, or that we wouldn't be able to tell the difference between which oak tree we planted. So it's implied that those oak trees are identical, or in this case, they're indistinguishable between them because they're all the same type of tree. So we have to think about how many total items do we have. So we have 20 total trees. So if they were all individual and all unique, it would be 20 factorial. But because some items are identical, we have to divide. So 6 factorial for the 6 oak trees, 9 factorial for the 9 maple trees, and then 5 factorial for the 5 poplar trees, which in the end gives us 77,597,520 ways. So there's still plenty of ways that we can arrange these, just obviously not as many if they were all unique. Five, consider the word baseball. How many permutations are there in the letters of the word? So again, we have to think about, okay, in baseball, how many total letters do we have? We have 8 letters. 8 factorial. There are 8 letters. But we have 2 A's. I'm just writing it up here because this will apply for all the other following questions. So we have 2 A's. We have 2 B's. That probably should have been first. 2 B's. And we have 2 L's. So we have some identical objects. So it's not just going to be 8 factorial. We are going to divide by the 8 factorial by 2 factorial times 2 factorial times 2 factorial. Right, so again, even though we don't show the multiplication, it's implied that it's 2 factorial times 2 factorial times 2 factorial, or 2 times 2 times 2. And in the end, we will have 5,040 ways that we can arrange these letters in ways that would be, you could argue, unique, right? They would be distinguishable ways. How many are there if the word must start with B? So the word must start with B. So let's think about this without worrying about any of the restrictions in terms of the identical letters or the identical objects. So the first one has to be a B. So there's only one option for the first one. Then in our 7 remaining spots, 1, 2, 3, 4, 5, 6, 7, we have 7 letters. So 7, 6, 5, 4, 3, 2, 1. So that's the distinguishable ways, or not distinguishable ways. That's how, if they were all unique letters, that's how we would arrange them. So we would essentially have 7 factorial ways to arrange these letters if the word must start with a B. But now what we have to take into consideration is, okay, of the letters that I'm arranging, do I have any that are identical? And in this case, we do. We have 2 A's still that we're going to be rearranging. So we have to divide by 2 factorial. And we still have 2 L's that we're arranging. So we're going to divide by another 2 factorial. They might say, well, what about the B's? That's true. However, because we have a B in a specific location, we're not going to be arranging it with another B or in a different spot. Right? There's only the one B that we have, that we start with. There's not 2 options. There's only one B available in that first spot. Right? And again, you could imply that, well, that takes care of that repetition. So there's a B in the first spot, so there's one of them. And we have the remaining ways. Now, if you did say, well, there are 2 B's actually, there are 2 possible options, right? I would argue no, because we don't know, there wouldn't be a difference. So there's only one, but then if we said that there were two there, then we would have to divide by a 2 factorial to get rid of those two b's. But because that one spot is taken care of by one b, there's only one option for that spot. Then we end up with 7 factorial divided by 2 factorial times 2 factorial, or 1,260 ways that we could arrange these letters. Now, how many are there if the word must start and end with an L? So same idea. Let's look at how this would look without the restrictions, or with assuming that all items are identical, or not identical, are all unique. So we have one L in the first spot, 1, 2, 3, 4, 5, 6, 7, 8. One L in the last spot. Again, whether you argue that, well, I could have two L's possible for the first one, it's just easier if you think of it as just one option. One L for the first spot, one L for the second spot. Then we have 6 times 5 times 4 times 3 times 2 times 1. Oh, we have one too many spots. 1L. So in this case, it'd be 6 factorial, because there's 6 items that we're arranging, and then the 2 ones on the end, divided by, we still have identical objects. So we still have 2 A's, and we still have 2 B's that could be in different spots. Again, if you decided to say there were 2 L's that could be possible for the first spot and one for the second, then you would have to divide by another 2 factorial, because those 2 L's, the order doesn't really matter. So we have then 6 factorial divided by 2 factorial times 2 factorial, which would give us 180 ways. What if it had to contain the word ball? So if we had to have B-A-L-L as a word, so those have to stay together, B-A-L-L. So then we have, it's 8 factorial, and there are 8 remaining letters. Or sorry, 4 remaining letters or 4 remaining spots. Again, keeping in mind that this moves. So that means that there's actually 5 items, or 5 factorial. Now you might say, okay, well, what about any words that repeat? Right, or letters that repeat? Well, we have 1B, 1A, and the 2 L's in the word ball. So they're already taken care of. They're moving through with that. They can't be rearranged. They have to be in that order. In the remaining options, so another B, another A, an S, and an E, do I have any identical items in those letters? In that case, no, we don't. We don't have any repeats in B, A, S, and E, so it's just going to be 5 factorial, or 120 ways. What if it starts with the word ball? So similar to D, ball is together. However, in this case, it's not moving. So that means we just have the 4 options after it. That ball is staying at the beginning. So in this case, then, it's just 4 factorial. So the 4 remaining objects or remaining letters are going to be arranged in those 4 remaining spots to give us 24 ways. And then lastly, consider the word baseballs. Right? So slightly different. We added an extra S. So it's still starting with the mini word ball. So we're starting with ball. It's not moving. And we have 5 remaining options. So B, A, S, E, plus that last S. So in this case, we still have 5 factorial. So 5 options that we're arranging. But we have two s's now, so we have to divide by 2 factorial to take care of those two identical s's that could be in different spots in those 5 remaining slots. So 5 factorial divided by 2 factorial gives us 60 ways, or 60 arrangements. So the key thing here is now when we're dealing with order and we're looking at permutations with identical objects, if they're identical, then the order of those objects or the placement of them doesn't really matter, because it's not really going to change the appearance of the arrangement. So we have to account for those identical objects because the order of those objects wouldn't really matter. So we do have to divide by the factorial of how many identical objects there are, and this could apply to multiple sets of identical objects in our overall set of items that we're arranging. So again, this is just going to bridge the kind of 2 units between permutations, which was the previous unit, and combinations, which is what we're going to go into.